Now the first thing that we can do is describe the motion from, say, position versus time diagram, and then demonstrate the same motion in a different diagram, v versus time. And then since we're at it, we could even extrapolate the acceleration versus time diagram. Let's see how that works. Let's imagine I start with this, and this, and this, and then something like this. Let's call this point A, let's call this point B, C, D, and E. This is a straight line horizontal between A and B, between B and C, a straight line positive slope, between C and D, straight line negative slope, and between D and E, again, we'll assume it's a function proportional to x to the power of 2. So from A to B, obviously I'm not changing my position. The position stays the same, therefore my displacement stays the same, which means that my velocity must be 0, which is confirmed by the fact that this has a slope of 0. Therefore, my velocity is 0 between A and B. If my velocity is, whoa, let's do things carefully here. Okay, so 0 right here. And then, whoa, well, it doesn't like my 0. Okay, let's imagine 0. Now, if my velocity is 0 here, then 0 here, then 0 here, my velocity is constant, which means that my velocity doesn't change. And if my velocity doesn't change, I know that my acceleration is 0. Therefore, in my acceleration versus time graph, it is also equal to 0. So those three graphs between A and B describe the same motion. One in A versus t, the other one is v versus t, the other one is x versus t. Now let's look at B versus B and C. Between B and C, I'm changing my position. My position changes from this value to this value to this value to this value, all the way up to this value. So I'm changing my position. How am I changing that position? I observe that this is a straight line, therefore I'm changing my position at constant rate, which means that my velocity is constant. So now I'm cruising with a particular velocity, which I can obtain by calculating the slope carefully between B and C, in a positive direction because the slope is positive. And I'm doing it, if I haven't already said it, at constant speed. So I know that my velocity has a particular value between B and C in the positive direction, and I know it doesn't change. So let's imagine that the slope is 2 between B and C. If the slope is 2, I know that my speed is 2. It's positive 2, therefore I know that my velocity is positive 2 in the whatever positive direction. So if I want to describe this motion in my v versus time diagram, if my slope is 2, positive 2, then my velocity is positive 2, and it doesn't change. Therefore, I have an horizontal line. Okay, again, I have a horizontal line because the velocity doesn't change. The slope at this point is the same as the slope at this point, is the same as the slope at this point. Now, if my velocity is 2 at this instant, then 2 here, 2 here, 2 here, and 2 here, it means that it doesn't change. My velocity is invariant, it doesn't change, therefore my acceleration must be 0. Hup. Now, from C to D, I'm changing my position, but this time my position gets smaller and smaller and smaller. How? I notice that this is a straight line, therefore the rate at which I change my position is the same. And the slope will give me the rate at which I change my position, which again is my speed or my velocity. So the magnitude of my slope will give me the speed, and I notice that my slope is negative, therefore I know that I'm going now in the opposite direction. So let's imagine that now this slope seems to be a little bit less than the previous slope, so let's say 1.5. So I know that the magnitude of my direction is 9.5. Since my slope is negative and I'm going in the opposite direction, therefore I need to pick minus 1.5. And the slope between this point, this point, this point, this point is the same, therefore my velocity is constant, whoa, at minus 1.5. Again, if my velocity is constant, my acceleration must be 0. Now, last segment, I'm going from D to C. Obviously, I'm increasing my position, and the rate at which I'm doing it increases as well. So I know that I'm going to increase my velocity at a constant rate. And this will become a straight line. Now, it is not very clear how I came up with this. Let's look at the mathematics. Remember, V is equal to magnitude dx dt. So to obtain the velocity, all I have to do is take the first derivative of my position, which I will write x dot. If my position, x versus t function, is proportional to x2, then obviously my velocity, which is the first derivative of my position versus time, must be proportional to x to the 1. That's how I know it's a straight line. And that's why I assume, and I mentioned several times, that whenever you see a nonlinear function in x versus t graph, you can always assume it's x to the power of 2. So when you take the first derivative of x to the power of 2, you know you have to obtain x to the power of 1, which is a straight line. So you know you have to have a straight line. The slope of that straight line will depend on the factor that is in front of the x2. So in order for us to know this particular value, we need to, take points very carefully on that graph and deduce the functional form of this portion carefully. As far as I'm concerned, I'm not really picky about getting the exact slope. All I'm after is that you're able to realize that if you have x to the 2 for x versus t diagram, you have to have an x to the 1 or a straight line for v versus t diagram. Now whether you choose this slope or this slope or this slope, I'm not so much concerned about this. I'm only trying to sketch and have you sketch those behavior. So now that we know that we have a positive slope, we can deduce our a versus time diagram if v increases at a constant rate. We know that the slope of a v versus t is the acceleration. Therefore, let's say if the slope is 2, again, then we know that the a versus t is 2 right here. If you had this, then you know that your velocity starts very high, then gets smaller, smaller, smaller. So you would expect something like this instead, going down. Don't worry about those jumps. Those jumps refers to every time you have a kink. The same way as we went from x versus t to v versus t to a versus t, you should be able to go again in the opposite direction. If every time you go in this direction, you have to take the inverse derivative. So obviously you're losing information. If you go in this direction, if you're careful and look at every point, you should be able to get this very precisely. because you're taking derivative. So remember, whenever you're going from x to v to a, you're doing derivative due to the functional form of velocity and acceleration. If you're going backwards from acceleration to velocity, velocity to position, obviously you have to do integration, which means that you have to be told the initial boundary condition. If not, and you being asked to sketch it, then you might lose information here and there.